Example 1 from Key et al. 2014 uses relational and conditional operators in order to operationalize and create the decision rules to produce a decision set for Kudzu. So it's based on previous studies about Kudzu in the 1970s. Table 1 here is the critical table. It produces both a factor and constraint. We have the number of frost-free days greater than 146, mean annual precipitation greater than 1,500 millimeters per year. So for frost-free days, wherever a cell has a number greater than 146, it will become a 1. Otherwise, it becomes a 0. So the 1 is the factor and the 0 is the constraint. Mean annual precipitation, likewise. Anywhere greater than or equal to 1,500 millimeters per year will receive a 1. And otherwise it will be 0. And then they show a Boolean AND operation. So that's multiplied. 1 times 1 is 1. 1 times 0 is 0. So this is the intersection or Boolean AND. So the conditional AND operator. As I mentioned in the previous module, AND and multiply for Boolean layers are the same thing. So for these two factors, we put them together as such. In a cartographic model, we have our inputs are the days greater than 0 degrees Celsius. And we're interested in 145 days. So we say greater than 145 days produces a intermediate raster called greater days 1, for example. Then precipitation in millimeters greater than 1,500 or equal to, I should say greater than or equal to 1,500, equals greater than precip, EC1, intermediate layers. So these are the intermediate layers that we don't see. Then we combine them either with multiply, or more strictly, we want to use Boolean AND in this case. And that produces then the decision set, Kudzu suitable. Everywhere with a 1 is suitable. Everywhere with a 0 is not suitable. In map algebra, we can do this in a single statement. Kudzu suitability, we have rain as the raster variable for precipitation in millimeters, and temp as the raster variable for days greater than 0 degrees Celsius. Then we simply say in a single relational and conditional statement, rain greater than 1,500 or equal to, and temperature greater than or equal to 145. And that produces this map here. And we know this is a very bad representation. How do we know that that's a very bad representation? Because it doesn't even coincide to where Kudzu is currently found and observed in the United States. So you know your model's bad if it cannot even reproduce the current reality of things independently. And by independently, I mean this model doesn't contain any information on the current locations of Kudzu. And since it has no dependence on the current locations of Kudzu, this is an independent model, it has variables, factors that are independent of the observations. And a good model will at minimal reproduce where the observations are actually found currently, the majority of them in any case. And this doesn't. So the predicted distribution is not great either. Now, in terms of sensitivities, we're using a conditional AND we're using constraints and value thresholds here. And changing the critical thresholds, this value or that value, will change the output. And so we know exactly what will change the output here in this particular model, and that's these particular values. So one way we could improve the model would be, for example, sampling the number of frost-free days and mean annual precipitation where we find Kudzu currently, and then setting those as the constraint values. Then we should have a model that would better reproduce the current distribution of Kudzu. And then we could apply that to future conditions as well. If we have a future climate surface and a future that has frost-free days and precipitation included in there, we could then use that to see how the species would potentially find new candidates from the candidate set to add to the decision set. In other words, how it would expand or contract in certain regions. The first model that we're going to attempt is the first model of Key et al. 2014. That model looks at strict thresholds to determine the number of growing degree days greater than or equal to 146 and precipitation in millimeters greater than or equal to 1500 millimeters. To do that, we have to start by preparing our data. So this is the data step, and this data step is common for all three models. We'll just do it once. So in the Kudzu GDB geodatabase, we have Kudzu data, and in there we have a boundary, which we'll bring in. That defines the boundary of the study region, which is the continental United States, excluding Alaska. And then we have climate, and we'll bring that in. The climate data, as you can see, are point data. So they have to be interpolated. I'm going to go to my Geoprocessing tab, Toolboxes, down to the Spatial Analyst tools. And in Spatial Analyst tools, we have interpolation. And in there, we'll see a topo to raster. Now, there's two tools called topo to raster. One is topo to raster, and the other one is topo to raster by file. We're interested in the topo to raster one. Now, before we do anything with that tool, we're going to set whatever environment properties we can right now to control our raster output. Presently, we don't have any raster layers, but we do have a boundary. So this boundary here, which is we'll just call it the United States boundary, that can at least be used as an extent and a mask to start with. So we go to our Analysis tab, Environments. We'll set the output coordinate system to be the same as boundary, the extent to be the same as boundary, and the cell size, we're going to be doing cell size of 1,000 meters by 1,000 meters. That's our cell size that we decided to do this with. Any cell size projection method doesn't matter here because we're not doing any projections, but just change it to preserve resolution. And then mask, boundary. We can't set the snap raster yet because we have no raster. And once we have a raster, after the interpolation, we'll go back here and reset everything to that new raster layer. So I'll start with the precipitation. So I'll go to topo to raster and open up that tool. In the topo to raster tool, the feature layer will be climate. So I'm going to choose climate. And then I choose the field that contains the climate data that I want to interpolate. And here, I'm going to start with precip annual so mean annual precipitation. The type of data this is not contour because we can see individual points. And so we're going to call these point elevations. The output raster, I'm going to call it precip mm. Notice the cell size is already set because that came from the environments. The output extent also came from the environments, and that's already set. The only other thing we have to change here, in this case, will be the primary type of input data. Again, it's not contour, but spot. That's a spot elevation, or points. And again, elevation here means mean annual precipitation. And then I click Run. Once it's finished running, it adds the precip mm to my contents. And I can see here, precip as a raster layer. So what I want to do next is go back to my environments and now use this raster layer to control the properties of the next raster layer, which will be the days that are less than 0 degrees Celsius. So output coordinate system, same as precip mm. Extent, same as precip mm. Let me scroll down a bit here. Cell size, same as precip mm. Mask, same as precip mm, and snap raster, same as precip mm. And then we click OK. So now precip mm will control the output of any tool in ArcGIS Pro, including our second run of the topo to raster tool. So going back to geoprocessing, topo to raster again, my feature layer will continue to be climate. The field this time will be days less than 0 degrees, which is the field DLT 0 deg. The type again has to be the same thing as a point elevation. Then the output will be days LT 0 gig, like that. Days less than 0 degrees. The output extent is taken from the environment settings now, which is precip based on precip mm. And the other thing we have to change here is the primary type of input data to spot for points. And then we click run. And it can take anywhere from, less than 10 minutes to more than 10 minutes. It's a very computationally intensive algorithm. The algorithm used here, ANUDEM. After a wait, we have the days LT 0 deg. That's days less than 0 degrees Celsius. The next thing we have to do is convert the days less than 0 degrees Celsius into days greater than 0 degrees Celsius. So for example, right now down in Florida, we have a pixel value of 0 because there are 365 days. There are 0, in other words, there are 0 days less than 0 degrees Celsius. And as we get up more northern, let's say up to Maine and whatnot, we'll have values up here of 197. So 197 days less than 0 degrees Celsius out of 365. So what we need to do then is subtract 365, or subtract this raster from 365 days. So in geoprocessing, I'll just go back and I'll go find my math tools and minus. The input raster will be days less than 0 degrees Celsius, but that will be the second input raster. The first one will be a constant raster with a value 365, like that. So that means 365 minus each cell in the days less than 0 degrees Celsius. The output then will be days GT 0 deg. So days greater than 0 degrees Celsius. There we go. Now if I look down and click down here in Florida, for example, I see 364.3 days in that particular location. And then up here, let's say in the northern Maine, I get 166. So there's 166 days greater than 0 degrees Celsius there. So now we have both of our rasters that we require for analysis. And I'll remove the old one, days less than 0 degrees Celsius. Here, I'll remove it. So now let's put the rest into a model, a basic cartographic model. So I'll go back to my catalog. And in the Kudzu geodatabase, I'll right click and say new toolbox. I'll call it KUDZU models, like that, Kudzu models. So in my Kudzu models toolbox, I'm going to right click and say new model, and that will open up the model window. Both of these will be inputs, so I'm going to bring both of these into my model builder, the days greater than 0 degrees Celsius and precip mm. Now I know what I care about here is finding where we have greater than or equal to 146 days. So I need to go back to my geoprocessing, math, and I'll need a greater than or equal to. So I'll go to logical, greater than equal to 146. So greater than equal to, and then I'm going to join my days 0 deg here to my greater than equal as the input constant value 1. Then I'll double click on greater than equal, put in the second comparison value here, which will be 146. Click OK, and then rename that constant to 146. Then I'll call this here the output. Even though it's an intermediate, I'll just rename it to temp factor. So that's the temperature factor right here for this model. And then for precip, I also need a greater than equal. So I'll drag one in here, join precip to greater than equal as the input value constant, input raster or constant value 1. Then go in here, put the second one, which will be 1500 millimeters. 1500. Click OK, and rename that 1500. So I know what's in that particular argument. Now, I want the intersection of these two things. And that means I need a Boolean AND. So I'll bring my Boolean AND here. Join these as the two input rasters. The output raster will be renamed to suitable. And I'll say suitable underscore bool for Boolean. So our decision rule here is a Boolean AND. Then I'm going to just auto layout and fit to window like so, and then save my model. I'll also right click on the suitable bool output and say add to display. So it automatically will be added to the display. Then I can look over my model quickly just to make sure everything is correct. So days greater than 0 degrees Celsius, we're interested in greater than or equal to 146 of those. And precipitation, mean annual precipitation in millimeters, we're interested in 1500 millimeters or more, greater than or equal to that value. Then we have our intermediate data right here, the temp factor, and I should actually rename this one so it's more readable, the precip factor, like so. And then that goes into a Boolean AND, and so does temp factor, so that's the intersection of both of these. Now I'll click run. And we can watch it running each one of these processes. And then we see the drop shadows that tell us that the model has run successfully and is presently in a already run state. Then I'll click on my map to have a look. Well, this is the prediction based on those very hard boundaries or precise thresholds. And it predicts over here on the west coast is good for Kudzu. It's very wet there, and pretty much has all frost-free days. And again, in Texas, Louisiana, northern Florida, and then again over here by Miami, and a few places in here as well, and even up here would be suitable, and that both of these have more than or equal to 146 days frost-free and 1500 or 1.5 meters of precipitation a year. To see how well our model matches reality, I'll go back to my catalog and I'll bring in the Peoria, Montana layer. This is the actual observed locations of Peoria, Montana in the US. And right away we see that our model is not good. If our model was good, it would at least predict the majority of the current locations of observed Peoria, Montana, which are the points here. Whereas even where there's the highest clusters of these, it doesn't even show those zones very well. So in these regions here, Georgia and whatnot, shows there's some potential there, but not as much as we observe. And then of course, all the way up to, the Windsor-Detroit corridor here, and all the way up to, past New York, past up to Boston and stuff like that. We also have observed Peoria, Montana, or Kudzu, and the model doesn't predict that. It only predicts where you see the purple here. So it's not a very good model. How could we make that a better model is a question. So one way to make this type of a model at least match reality would be to sample the raster layer for precipitation and the number of days above 0 degrees Celsius, to sample those at the locations of the current Prairie, Montana, and then look at what the maximum values are in each of those, and use those as the means by which we could predict the output as new thresholds based on the observed data. And then we'll see if there's anywhere else that match those conditions as well. So that's a different exercise, which you won't do, but that's how you would approach this type of a question. Is first you want to get a model that will be based on the actual data that we observe. So where we observe Prairie, Montana right now is in all these green dots. So we would get the precipitation for each green dot and look at the maximum, or maybe the 95th percentile of that precipitation. And then that value could become, instead of 1500 millimeters, whatever that value is, would be replacing 1500 millimeters. And likewise for temperature, or in our case, temperature is the number of days above 0. And then we might find that we have a better suitability map, since it would probably match what we observed much better, and even show other areas that have those same combination of conditions where we find observed Prairie, Montana. We can do the same process and same model using Python. So I'll click on my Analysis tab, and then Python to open up my Python window. Since this is the first time I'm using Python in this session, I'm going to use my standard imports. I'll say from arcpy.sa import all, and also my environment settings. I'll say from arcpy import env, just so I can check that the environment settings have been passed down to the window from the global environment. I'll say env dot cell size, as an example here, and it gives me my C data Kudzu precip mm. So that's just to check one of them, and if one of them works, that means all of the global environments have been passed down to the Python window. This is a very important step, because if you don't test whether they've been passed down, sometimes they're just not passed down. And that's a bug in the software. So it's always good to check. So if you type env.cellsize and you see nothing here, and you know that you've saved your environment settings in the global environment here, all to that control raster precip mm, and they don't show up here, just nothing happens when you type env.cellsize, then you need to save what you're doing, close and reopen ArcGIS Pro, and then try it again. So that being said, let's make two raster variables to make this easy. I'm going to call, I'll make one called temp, and that's going to be equal to raster, and that's raster is going to be my days greater than 0 degrees Celsius, like so. And then a second one I'll call precip, that'll be equal to raster, I'll let it take it from here, precip mm, like so, enter. So now that we have those two variables as raster variables, we can complete the model in one statement. I'll call it suitability two, or just suitability two, right there, equals parentheses and parentheses, like so. And in the first parentheses, I'm going to have precip greater than or equal to 146, and, or not precip, that should be temperature. So for precip, that should be 1500, and temp greater than or equal to 146. And I'll hit enter. Oops. It says it's unable to open the mask raster precip. So I'm reading this error, and this is not a something I planned. This is just an error that happened. So it says the issue is in greater than equal to, and as I go all the way down, I always want to go down to the last error here because that's usually the most informative one. I get runtime error, this number, and then it says unable to open the mask raster precip mm. So that means there's an issue with that mask raster, and that's in the environment settings. So what I'm going to do here is I'll just say env.mask equals precip, precip, like so. Then I'll run that last one again. So by reading that error and knowing where the issue is, it's talking about a mask raster, I know that is a setting that is in environments. So for some reason, it didn't pass down properly the environment setting for precip. And so I set it here in my Python window explicitly. Now that is going to stay as the mask until such time as I either change it in Python or reset my environment settings. And I'll reset my environment settings for now. So I'll say arcpy.reset environments. Then I have suitability 2. I'll have a look at it. I'll just close the window for a second for Python. And there we can see suitability 2 and suitability 1, and they look identical, except maybe a little bit up here. No, it looks the same. So they both look the same. It's pretty obvious here, but again, sometimes when you're working with pixels and many pixels, it's easy to find one or two that may not be the same. And so I'm just going to check that by doing a difference map. So a difference map here will be, I'll say D equals suitability 2 minus raster, and that will be suitability bool. And again, it says unable to open the mask raster precip mm. That's because I reset my environment settings, and so that same error comes back. So let me go to environments and try to reset it there. So mask raster precip mm, like so. Okay, I'll try it again, see if it fixes it. Nope. So I'll have to do that here again, like this: env dot mask equals precip. Then I'll run my difference. So that time I did that on purpose to show you again that process of reading the error, figuring out what it is, it's the same error again, how to change that so it's properly going to work in Python. And we have to remember that at this point in the Python session, or in Python for as long as I keep this program open, in the Python window, precip will be the mask. Even if we change things under environments up here, the mask will remain precip. So it's always a good idea to reset your environment settings or something afterwards, but in this case, we won't, because we'll be doing another modeling here, so we'll need it like that. And then we have a distance, or I should say a difference map of 0 everywhere. So everywhere is 0, you can see here. There's just some artifacts of the screen drawing you can see in here. Those aren't part of it because we see it in the legend right there. We see something other than 0. So we get the exact same results from both the cartographic model and the map algebra approach. And we would expect that. We've seen that many times now.